So this is Dr. Kevin Yager. Kevin is a group leader of the Electronic Nanomaterials Group in the Center for Functional Nanomaterials at Brookhaven National Laboratory. This is a Department of Energy facility located on Long Island, I'm pretty sure. The island that is Long. It's a massive facility. It has some of the best characterization and growth tools in the world. If you're a materials person, it's a great place to go visit and check out and see what's going on. And Kevin is going to talk to us about a really interesting new tool he and his team have created called QPress, which will let you make a sandwich out of layers if you're still hungry after that very filling lunch. So Kevin, I will let you take it from here, however you like.
Okay, great. Thanks a lot. Yeah, and it's my pleasure to present. Sorry I couldn't be there in person. And thanks to Shauna for giving such a good talk prior to mine. I think she laid out a lot of a lot of the things that are kind of underlying what I'm going to show. So it's like good to, she showed a bunch of examples of what 2D materials actually look like when resolved atomically. So that kind of sets the stage very nicely. Okay, so yeah, just to sort of build on the introduction that Patrick just gave me. So I work at Brookhaven National Lab, which you are correct. It's on Long Island. It's close to New York, but not that close. It takes some time to get between them. But it's this big facility, and you can see in the background image here, you can see all the different departments of Brookhaven. There's a particle physics ring up here. There's this X-ray light source here. This is the nano center. This is the building I work in. So lots of different things happening on site at Brookhaven, and I work in this facility called the Center for Functional Nanomaterials. And so we're really focused on how you can make better nanomaterials, how you can measure nanomaterials, all of that kind of stuff. And what's important to understand about the CFN, where I work, is that we're funded by the Department of Energy to be what's called a user facility. And what that means is we don't just do our own research. I mean, we do research like the good scientists that we hope we are, but we also try and build facilities that are available to the whole world or available to the community. And so the idea is that any capability that we have in-house is something that should be available not just for us, but for everyone else. And so the QPress, which is what I'm going to tell you about in my talk, is one example of one of these facilities, a unique capability that we built because we were interested in it, but perhaps more importantly, because we wanted other people to use it. And Patrick and Sean are some of those people. So that's kind of like the background. And I won't dwell on it, but I'll just give you some examples of other things that happen in the CFN, because we're meant to be this facility that provides access to the whole world, to all these frontier capabilities useful for nanoscience or material science more generally. So, for instance, we have synthesis and characterization labs. We make nanoparticles. We do thin film deposition. We do synthesis of novel films on surfaces. We have a nanofabrication facility for doing that kind of stuff. And then we have a whole suite of characterization tools, and some of them are, sort of quote unquote off the shelf. We buy it from a vendor and we just operate it. But some of them are a little bit more sophisticated or sort of customized. We sort of adapted it to do exactly the kinds of things we wanted it to do. So, we have things that run the gamut from proximal probes, meaning AFM and STM, which Shauna just talked about. Optical methods, we have some really nice electron microscopes, X-ray methods. And then we also have a theory and computation group that exists to help couple, synthesis and characterization to theory and simulation methods. And so that's kind of another capability that we offer. And so you can see from this that we try and offer the whole portfolio of things that someone might want to do in nanoscience. Okay, so that's kind of the general overview of what the CFN is. And just to keep in the back of your mind is that if any of the things I'm listing on this slide or later in the talk are things that you think could be interesting to you or someone else, then feel free to reach out. If you're just interested to learn about them, you can come visit Brookhaven. If you're ever working on a research project that intersects with any of these things, then all these capabilities are available for free for people to come use. Okay, so now let's talk about two-dimensional materials. So I'll give some sort of general introduction to 2D materials first, and then talk about the QPress, with the warning that I'm not really a quantum materials or 2D materials person by training. I've gotten into it over the last few years, but I'm not the world expert in these materials, but I do find them very exciting for a bunch of reasons. So the canonical example of a two-dimensional material is graphene, which probably you've all heard of. So, graphene is this single layer of carbon atoms that are, bonded into this hexagonal lattice. So carbon can take many forms, right? Diamond is one example. Graphite is another example, which is layers like this that are sort of like stacked on top of each other to form a crystal. But if you sort of separate those layers in graphite and pull off just a single layer, then you get what we call graphene, which is this atomically thin layer of carbon, which is very exciting. Nobel Prize in 2010 for isolating it and characterizing it. Graphene has these really interesting properties. It's considering how thin it is, it's remarkably strong, and people have even used it as like a window, like a membrane on like nano devices to like contain liquid, to separate one liquid from another or liquid from vacuum. So they're actually really strong considering how thin they are. They have interesting electronic properties, so you can even use them as like transistors and things like that. So very cool materials, but what's also interesting about them is in terms of making graphene, it's kind of remarkably simple how it can be done. And what I'm showing here is kind of the state of the art of how people actually make 2D materials in most labs. And it's literally with Scotch tape. Like you take off the shelf commercially available adhesive tape, and you do something like you sprinkle some graphite crystals on it, and you sort of press the tape into itself repeatedly. And in doing that, you sort of fracture apart these graphite flakes over and over. And if you do that enough times, you might get lucky. And in some areas, you're going to get graphite stacks that are quite thin, maybe even just like a monolayer thin. And so then you can take this Scotch tape and put it against a substrate, like a piece of silicon wafer, and rub it. And if you're lucky, again, you can transfer some of those flakes onto the substrate, and you peel off the tape. And again, if you're lucky, you'll be left with some really nice, clean, large flakes of the material you're interested in. And if you look around on the substrate, you'll find areas where they're really, really thin. Like they won't all be monolayers, but you'll be able to find some areas where they're monolayer. So if you're doing graphite, you'll find some areas where the flake is so thin, it's one atom thick, and that's graphene. So what the point I'm trying to make here is it's like incredibly easy to do, which is cool. It's good that you can kind of just in a few minutes make an atomically thin material. But as I kept saying, it's sort of relying on this this statistical notion of this get lucky notion, which is one of the downsides, right? You're really relying on just kind of the statistics of do it enough times and eventually you'll get the flake that you wanted. Okay, so what else can we say about 2D materials? Graphene is just one example. There's a whole zoo of possibilities. Shauna spoke about some of them in her talk. So you can see black phosphorus, chalcogenides, HBN. This is hexagonal boron nitride. So it's actually not a single component. It's two different materials that are forming this hexagonal lattice. These are some common ones. You can see some other examples shown over here. The point is that after people discovered graphene, they discovered there's a whole bunch of materials that are similar to it in the sense that the bulk crystal is layered, right? So there's one direction in which things are covalently bonded, and so it's really strong. And then there's another layer in which the layers are just van der Waals interacting. So there's no covalent bond between them. There's just these van der Waals forces holding them together. And so the interactions in that direction are weak enough that you can kind of split them apart in that direction. And with the Scotch tape trick, you can then get a monolayer of all of these materials, HBN, hexagonal boron nitride, black phosphorus, graphene, all of these different things. And each one of them will have its own unique electronic properties. And so that's extremely important, especially as we get to the next step, which is, okay, if you can make these individual layers that are each atomically thin, then people started thinking, well, what would happen if you start stacking these layers on top of each other, right? And so this, created this field of what's called heterostructures, hetero, meaning the different, so the different layers don't have to be the same material, but you can stack them on top of each other. And some people sort of liken it to sort of Legos, because you can choose any layer combination you want, right? Like all these 2D materials that exist, you can choose whatever material you want and put them in whatever sequence and whatever layers on top of each other that you want. And what I think it's important to think about is that this is it's a way of making a new material. Like the heterostructure is a new composite material, but it's not limited in the traditional sense. So if you think of the normal way you might make a multi-layered film, let's say you have some like gas molecules in the vapor phase and they deposit on a surface. So you introduce one set of molecules, they deposit on a surface and form some layer of atoms. And then you introduce a different set of molecules into vapor phase and they deposit on the surface and form a second layer. But you don't really get to choose how those layers go on top of each other, right? Like energy minimization, equilibrium chemistry is going to dictate what structure forms in that bilayer. So and in particular, there's this concept called epitaxy, where the layer that forms on top is going to want to register itself epitaxially with the layer below. And so if you're trying to put two materials on top of each other that have really different lattice constants, like really different spacings between the atoms, it's going to be hard to do, and it might lead to just a complete mess. And it might only work well if the two materials you've chosen have like well-matched unit cells, crystallographic unit cells. So that's a limitation of conventional methods. But when you think about these 2D materials, you don't have that limitation. You can pick any 2D material and stack it on top of any other 2D material, and they can't stop you. The materials are just going to go on top of each other and form that stack. So you can get really, really complicated and arbitrary about what you choose to build. You're not limited by conventional chemistry. And as Shauna already alluded to, you can not just stack control the layer order, like what material goes on top of which other material, but each time you put down a layer, you can in principle choose the twist angle between them. And that twist angle can actually have a lot of interesting properties. So one of the fundamental reasons we care about these heterostructures is when you put one material on top of another, they're going to affect each other's electronic properties, right? So they're going to modify each other's energy levels for all the electronic interactions in that material. So they modify each other. And as you can see here, if you put two materials on top of each other and introduce a twist angle, that modification will be different because the way the atoms in the two layers line up with each other is different. So in fact, you can even put the same material on top of itself, so like graphene on top of graphene, but if you control the twist angle, you can modify the electronic properties of that bilayer. And so people have shown these amazing things where just by changing the angle between the two layers, you can sort of tune through all these different electronic states. And so in principle, you could imagine having two layers you put on top of each other, and by twisting it, you tune it between being an insulator and a conductor, or ferroelectric for some angle and a superconductor at other angles. And people have discovered for certain layers, graphene on top of graphene, there's certain magic angles that give really unique, interesting electronic and quantum properties. So that's, and this is an image of that Moiré pattern that you heard about on the last talk, where the twist angle creates this different kind of interference between the atomic lattices in the two layers. And so you get this sort of supercell structure that has a length scale larger than the atomic lattice. So very interesting structures that again, we can control very arbitrarily. Okay, so I've sort of talked as if it was a given that you can just kind of stack layers on top of each other. In practice, how do you actually do that? So I showed you before that you can use Scotch tape to exfoliate single layers, so from a bulk crystal to peel off individual layers of these materials. But if you have two different materials, how do you put them on top of each other? And there's a bunch of ways of doing it, but I'm just going to sort of talk about one that's commonly used, and that's essentially use adhesives again. So in this example here, you have a glass slide, and then you have a layer of PDMS, polydimethylsiloxane. So this is like a soft, squishy polymer that just acts as a sort of like stamp, or like just a shock absorber, if you will. And then on top of that, you put some sort of polymer that's going to give you some adhesive properties, like polycarbonate, or there's a long list of different polymers that people choose for this, depending what adhesive properties they want. So you build this little structure like this, and then you press it into a surface where you've already put your monolayer on. So in this example here, there's an HBN, boron nitride, and you press down into it, and you sort of make contact, and then you wait a little while, and you maybe tune temperature a bit, and then you pull the whole assembly up, and you hope that you've peeled up the flake with you, and then you can go to a different substrate that has a flake already on it, and do a similar procedure and press your flake on top of that existing flake, right? So you could pick up an HBN and then go over to a different substrate that has like a graphene on it already, and then press that HBN on top of your graphene. And you can see these diagrams here, what that might look like. You sort of press down with this stamp system you have, make good contact, and then you maybe increase the temperature so that this adhesive layer becomes like more fluidic and less adhesive, so that when you pull up, you sort of peel away the adhesive and the flake is left behind. So when you peel up, then this flake that was originally stuck on the stamp is now left behind on the surface. And this is a pretty simple way of doing things, but it works remarkably well. And in the back of your mind, you might be worrying about certain problems like, well, isn't this like polymer going to leave some sort of like junk, some polymer junk in the surface? And the answer is yes. You might need to clean it or something like that. But again, the point is that it's a pretty simple procedure, and yet we're able to end up with something where we have atomic precision in terms of the layering. That's kind of the take-home message here. Okay, so just to sort of wrap up the intro part, One is that there's a lot of research interest in these 2D materials, as I mentioned, both in terms of layering them into heterostructures and controlling the twist angle between them, where you can control what properties they exhibit, and especially people are interested in quantum devices. And you can see sort of this exponential increase in the number of publications. Like people are really, really interested in 2D materials and in creating these kind of composite materials by layering them. So a lot of interest in the area. But one of the downsides in terms of making these, both making the flakes, the individual monolayer flakes, and stacking them into these heterostructures, the ways that I just described are really, in some sense, simple and elegant, but in another sense, they're very, very tedious, very manual, very error prone. And so they're driven by essentially graduate students in labs, great labs across the world that are working for a month at a time to build one of these structures. Like, just look how complicated this device structure is that they build, these different layers. And for each of these layers, they had to do one of these polymer stamping steps like I described. And if they get lucky, it transferred correctly. If they get unlucky, it didn't transfer, or it teared the flake, or it like destroyed the flake they were trying to press it on, or any number of things can go wrong. So to get one nice device so that you can do some interesting quantum measurements, which is what you ultimately care about, right? You ultimately care about learning something about the quantum material. To make one device can take, even a skilled person can take them a month, right? So it's like a lot of effort, a lot of work to make these kinds of structures. And so that's where the quantum material press idea came from. The idea of the quantum material press, or QPress, was we want to help people make these two-dimensional materials and make these heterostructure systems more quickly and easily, right? So we want to streamline the whole workflow of making the monolayers and stacking them. And for a couple of reasons. One, it should allow experts to tackle more challenging problems, right? Like in the past, they maybe were only ambitious enough to try a 2 or 3 layer system, but maybe if we make it easy enough, then they'll be able to build 10-layer, more complicated devices. But then also to lower the barrier, hopefully, for people who don't have as much expertise to start working on these interesting materials, right? And then, of course, there's also opportunities as you build a new tool to learn new things about the actual underlying materials physics of the processes, these sort of synthesis steps of making individual monolayer flakes and stacking them into heterostructures. So this was the dream that we had some number of years ago. We had this idea. We generated cartoons like this showing like, oh, wouldn't it be great if we had this like robotic automated system that could automatically do all the steps that a human does by hand, could automatically handle the tape, automatically handle the stamping process, and come up with these heterostructures. So that was the goal. And what I'm here to tell you is that we've made a lot of progress on that goal. So over the 2019 to 2021 time period, we constructed this QPress instrument, and you can see some photos of it here. And I'm going to show some more photos in subsequent slides, zooming in on these a little bit. So this tool now exists, and it's available for users to come start using. People have been using it. We're continually improving it, even as people are already taking advantage of it. And I think already it's sort of demonstrating that if you make the process simpler, you make it more robotic, more automated, more streamlined, then it's easier to make more complicated structures, and you can make them faster. So I think already we're seeing some evidence that this was worth it, that you can create more complicated heterostructures using the QPress than you could without it. That's the goal. Here's an example down here. Okay, so I'm going to take you through the sort of design of the QPress. You may never use the QPress yourself, but I think it's instructive to see what goes into kind of, when you think about this problem of like, I have a manual process that we're doing in the lab by hand, and I want to convert it into a more automated robotic process. All the complexity that you have to sort of handle when you start doing that, all the different things you have to think about. So that's the sense in which I want to sort of show you that this is the tool we've created to handle this particular problem. So at its core, the QPress is what's called a cluster tool. So these are, that's like a term used in industry to talk about a tool that is a connection of many different tools. And you typically have a robot in the middle that can move samples between the different stations. And so each station in the cluster can do something different. One might do material deposition, one might do thermal annealing, one might be some sort of measurement that you do to like confirm that the synthesis you did is working. And they're all coordinated through software because the robot can move samples from station to station. So that already speeds things up. But you need each of your individual stations also to be very streamlined and efficient for this to really be worth it. So here's a top view of the cluster tool, and this movie down here, you'll see some movies of sort of samples moving between the different stations to give you a sense. So like the core of the cluster tool is this robot that moves things between different stations. And what are the different stations? Well, we have these modules back here where you can store samples for like a long time. So people can come in, introduce their samples here, and then the robot can sort of grab them and do what it needs to do with them. We have a station here that can do conventional electron beam deposition. So this is just if you want to put down a uniform layer of metal on top of your heterostructures or as the base substrate for your heterostructure, something like that. We have a thermal annealing station over here if you want to do high temperature processing. But then the really most sophisticated part is this big box down here. And this is a big glove box. And what that means is it's like an airtight sealed box that we fill with an inert gas. So we use argon. And the idea with that is it allows all the operations happening inside here to handle air sensitive materials. So some materials like graphene are not air sensitive. You can work on them on the lab bench and there's no problem. But some materials are very air sensitive. If you worked on them just in ambient conditions, the oxygen in the air or the water in the air would react with it and destroy the material. So for those materials, you essentially have to work with them inside an enclosed environment like this. And so that's why we built this part of it to be this giant glove box, this giant enclosed inert environment. And that's also why we tried to make all the stations as much as possible sort of computer controlled so that someone can control them from the computer out here or even in a different building and know what they're doing, and they don't have to put their hands in there and kind of physically manipulate anything. So that's a design here. This is again a view of this glove box with the windows taken off, showing these different sort of custom modules that we have inside. And I'm going to explain what these custom modules are in a moment. You can see this video here of again robots sort of able to move samples around between the different stations. And the samples, by the way, you can see here, it's essentially, we use these silicon wafers, these 3-inch thin wafers that you can just buy commercially. They're similar to what's used in the microelectronics industry to make microchips, although now the microelectronics industry uses these really, really big wafers, and we're using these relatively small ones. But they're convenient because they're sort of a well-defined size that you can buy robots that know how to handle them. But you're not actually limited to that because, of course, you could take some other sample and just glue it onto, a wafer that's sort of a sacrificial support that you use to move around your sample. So not really much of a constraint, but that's sort of the design we chose. Okay, so I'm going to take you through these 3 custom modules. The first one is one that does exfoliation, so it automates the step of working with the Scotch tape. The second is what we call cataloging. So that's after you've put some flakes on a substrate, hopefully, you need to find them and make sure that they're good. And then the third station is what we call stacking, and that's where we're doing this polymer stamp step where you sort of build structures up layer by layer. Okay, so I'm going to take us through these 3 modules one at a time. And so the first is exfoliation. So just let me remind you what exfoliation looks like the traditional way, right? You put a crystal on a piece of tape, then a human with their hands kind of presses the tape together repeatedly in order to take that crystal and sort of thin it out into a distribution of a bunch of different flakes of different thicknesses and size. And so you can see them here. And then they take that tape and they press it onto a piece of silicon wafer and they rub. Some people rub with their finger. Other people use like some like tool to like rub. So everyone has a different sort of way of doing it. And it's very, some people are good at it. Some people aren't as good at it. There's sort of an art to learning how hard to press and things like that. And then they peel the tape off. And again, there's sort of an art to how quickly you peel the tape and things like that in order to get really nice flakes left over. And then when you're done, hopefully you end up with some nice flakes on the other side. So that's the manual process. So how can we make a robotic version of that process? And, you might think at first, well, maybe we need to have actual like robots with like hands and pick up the tape and do all of that kind of stuff. We chose to build something a little bit more simplified, but also more controllable. So what we do is we have this sort of roll-to-roll system where we buy, again, we're using commercially available tape because it works incredibly well. And we put this tape on this sort of roll-to-roll system so the system can turn those wheels and move the tape around to like bring in some fresh tape. And then what we can do is take a substrate and put it here. And we can start with a substrate that has, let's say, the crystal, the source material crystal, like let's say graphite, if we're trying to make graphene flakes. And then we can use this roller, which is on a motion axis that can press up and down. And we can sort of press down while we move the substrate back and forth. And that sort of simulates the same behavior as if a human was doing this tape to tape thing where they're kind of pressing it together. And it sort of transfers some of those flakes onto the substrate, between the substrate and the tape. And that already essentially, so you can do two steps. You can do one where you transfer from the graphite onto the tape and then bring in a clean substrate and transfer from the tape onto the clean substrate. And again, let's zoom in on this movie here. You can see in this movie, there's some crystal material on there, and we sort of approach it. We press down with the roller, and then we're going to move side to side to sort of, apply this this pressure to the flakes. And then we move here, and you can see here a bunch of crystals have been transferred to the tape from the substrate. And then we bring in this fresh substrate that has nothing on it, but you can see the crystals are on our tape. We bring it in, we press down, and we do another sort of rolling operation. And there's some flakes here. You can't quite see them from this angle. But when we do this rolling operation, hopefully some flakes are now stuck onto the substrate and we peel off. These were the flakes that we sort of transferred, and you can't see it very easily, but there's a bunch of flakes now on the substrate, okay? And the reason we're doing it with a robot is it can now be much more reproducible than if a human did it, right? So we can measure exactly what pressure we used, and we can use the same pressure every time. We can control the pull-off angle of the tape. We can control the temperature of the substrate, and it turns out that's quite important. So by controlling all of these parameters, we can tune it and optimize it for a new material to get really, really good quality transfer, which means like really nice flakes. And we're trying to get as many big, unbroken flakes that are thin as possible, right? So it's still a statistical process, but we're trying to make it more efficient than it was in the past, more efficient than the manual method. Okay, so that's, that was step one, robotic exfoliation to make flakes. And then you end up with these flakes on a substrate. Of course, you can't really, by eye, it's really hard to tell whether it worked or not. So what people typically do is they go in an optical microscope and they search around manually and hope that they get lucky and find a flake that matches what they want, that has the right thickness they want and the right size that they want, the right shape. So the automated version of that is instead we have this optical microscope that is can do these tile scans. So it essentially scans the entire substrate, every single spot. And then we use some simple machine vision software to identify the flakes. So it differentiates flakes from just like the background color. And it identifies them. And then we can compute simple things about them, like what's the average color of this flake. And with that information, you can start doing simple machine learning where you then say, okay, how many flakes do I have that are like of this type or this type or this type? In other words, you can classify the flakes and then later treat it as a database where you come in and say, okay, for that sample I just fabricated, show me all the large graphene flakes, all the graphene flakes that are bigger than 1 micron in size or something like that. And then you can sort of extract that information and take a look at it. So this is a faster, more efficient way of finding the good flakes because, this can run automated over lunch or overnight or whatever. You don't have to sit there and watch it. You can just look at the database at the end and kind of hopefully find the flakes that are relevant to you. And this microscope also has things like integrated Raman spectroscopy that can be used to confirm that if you have something that you think is a monolayer flake, you can use Raman to confirm whether or not it actually is indeed a monolayer. But you don't have to do it on every flake. And we've tried a bunch of different methods in terms of how you do these steps here, how you identify the flakes and how you sort of classify them and determine what they are. I won't go into it in too much detail today. Although it is quite interesting that these modern machine learning methods, deep learning, these convolutional neural networks you may have heard of, they can be used to do all kinds of fancy things like identify objects and images, like identify faces or dogs or cats. And so you can use similar technology to identify objects in scientific images. So in principle, you can say, oh, I want to identify flakes and I want to classify them. So this is a simple example where we were classifying flakes as, is this a graphene? In other words, is it like monolayer thin or is it something else like some polymer junk or a thick graphite or something like that? And you can see it works. You can get relatively high recognition on these kinds of things. So that's one way. Another way to automate things is to sort of use software, including machine learning. Although to be honest, for this problem, even non-machine learning approaches, like in other words, just more handcrafted software where you just find the flake and compute its average color, works reasonably well to find flakes. Okay, so the last custom module in this sequence is what we call the stacker. And again, I told you before about how people do stacking. They use this polymer stamp and they sort of press it into a surface, and there's different ways of doing that. people typically use these micrometer-driven stages that might be like hand-driven micrometer screws or some sort of motion stage with like where you're driving it with a computer to move up and down. So we're doing something similar, but we're trying to add a little bit more flexibility than other systems might have. So in particular, so you can see the different components here. We have this arm here that holds the polymer stamp. We have an optical microscope so that we can look through the polymer stamp, see what we're doing, and then we have this substrate. And both the substrate can move around, including in angle orientation, and then this stamp can move around because it's hooked up to this thing called a hexapod. And actually, let me go to this video. It's easier to see it zoomed in. So we're using this thing called a hexapod to hold the polymer stamp. And the cool thing about that is it provides arbitrary degrees of freedom in terms of controlling. So some motion stages, they can only go in one direction, or if it's a rotation stage, then they can only rotate about one particular axis. But this hexapod has 6 degrees of freedom. And in software, you can define, the center of rotation to be anywhere in space. You can see it's actually rotating around a point that's over here. And so you can translate and rotate in really arbitrary ways. And so this means you can get a little bit more fancy in terms of the motion profile you use when you're doing the stamping operation, and maybe try things that are more sophisticated than just up and down, right? You can try like rolling motions and things like that. But the basic idea is just a sort of automated version of what people have been doing in other labs, which is that you have this polymer stamp that has your flake on it. This is your substrate underneath, and you're going to basically press this into the substrate, and then can use temperature, round through temperature, and then peel off to transfer a flake. But you can also see the substrate here, the substrate holder can rotate in plane, and that's important so that we can make these twisted structures where you can, bring your flake and then sort of figure out what your angle is, and then rotate by the right amount to get that sort of bilayer angle that you wanted in some heterostructure. Okay, so those were sort of the custom capabilities we've built up over the last few years. I wanted to give you an example of how these capabilities have been used by some of the users. So again, this is a group, what we call a user group. These are people who are coming in to use our equipment. They don't work at the CFN, but they're coming in to use it. So this is Dawood Shashardi's group at NYU and his student Chijun, who came to work with us. And they, they're experts in making these heterostructures and measuring their device properties. So they know what they're doing, and they have a lot of experience in terms of how to make more clean interfaces, because I told you before that one of the downsides of using all of this adhesive tape and this polymer to do the pickup and the transfer is you have all of this organic material, these polymers and other organic small molecules, in the environment. And if those kind of introduce themselves in between your atomically thin layers, well, those are going to act as contaminants that are going to totally mess up your device properties, right? They're going to change the quantum properties, the electronic properties. So that's not a good thing. That's not desirable. And so, what they've been studying for a while is like, how can you make cleaner interfaces? And so they came to QPress to use our setup to more rapidly test a bunch of possibilities and try different options in terms of how you do that final stacking step. And one of the things they were able to find is that in that final stacking step, if you use the right kind of pressure and temperature regime, so you're pressing down with the right force, and not just the right force, but sort of the right rate, of adding that force, and also using the right temperature for the substrate, you can kind of like squeegee out the defects or the organic residue that was stuck between the layers. So in other words, you still end up with some residue, some junk in between the layers, but you can sort of get rid of it by pressing down and sort of you can think of it like when you put a film on your protective film on your cell phone, you sort of put it down and you like apply a motion that goes from one end to the other to sort of like wipe out all the air bubbles that got stuck underneath. And this is sort of similar, but at the nanoscale, where you're trying to like push out the residue and get it out so that you have a large clean area that you can use for your device measurements. And this image here is uniform green color, which looks boring, but it's actually very exciting, because what it means is that there's no heterogeneity. Like this whole area that they imaged here with this Raman spectroscopy, it's uniform, right? And so that means that there's no local defects that would mess up a device if you built a device from this. So that's just an example of some users coming in using QPress to sort of push forward what they could do in their lab. So the last thing I'll mention is just that I talked at the very beginning about how the CFN has a bunch of other facilities, right? We do other things like surface spectroscopy and X-ray scattering and nanofabrication, all these other things that we do in the CFN. And so what we're trying to do with the QPress is not have it just be an isolated tool, but have it be connected to these other capabilities. So you could imagine making a sample in QPress and then transferring it over to an AFM or an STM to do measurements on it, or some of these spectroscopies here that are very sensitive to sort of see the electronic states in these monolayer or monolayer materials, or these heterostructure materials, essentially spectroscopies or optical spectroscopies that can measure things like that. And one of the things to note is that I told you before that we built QPress to be in this glove box. Like the whole system is each individual station is either under vacuum or under an inert atmosphere like argon. And so you might say like, oh, but doesn't that mean once you like pull out your sample and bring it to one of these other tools that it's going to be exposed to the air and get totally destroyed? And the answer is, well, we have this trick. It's called a vacuum suitcase. You basically hook up this little module to the side of the QPress and it gets filled with argon. You put your sample inside and you close it off and you bring it to your other tool, and you can directly couple it to your other tool and then open it and sort of pull your sample out and put it into the other tool, and your sample was never exposed to ambient environment. It was always like inside its protective little suitcase that was filled with argon, inert argon. So that's a trick for sort of being able to measure these materials at different tools without them ever being exposed to the ambient environment. Okay, so just to finish off, I think the outlook for QPress is, we've been building it up over the last few years and we're continuing to improve it, but I think we're starting to see that it's a very cool platform for playing around with 2D materials, for making 2D materials more quickly. The exfoliator can very rapidly, you can like sort of cycle through and do like one substrate after another very quickly. So you can build up big libraries of flakes more quickly and easily than you could do it if you were just doing it by hand. And so that's sort of accelerating research, we hope. We have a bunch of people that are using it in their own research, which is great to see. And it's not a standalone thing. We want it to be connected to other capabilities, other measurement tools inside the CFN, and other measurement tools at other facilities. So the idea of QPress is, again, it's connected to the whole community. We don't want it to just be something that lives on its own. We want it to be something that people take advantage of and sort of make samples of QPress and then bring them to their home institute and do additional measurements there. And so looking to the future, like I said this at the beginning, we sort of view that the goals of QPress are to help expert people, tackle more challenging problems, to do things that they couldn't do before, and then also lower the barrier to entry for people who want to like play with 2D materials and maybe weren't previously willing to invest the effort to build all this capability in their own lab. Now they don't have to. They can kind of come to QPress, but then go home and focus on the part they're more interested in, which might be like the quantum measurements or something like that. And we're doing some research. I didn't really talk about it today, but we're doing some research on the physics of exfoliation and transfer itself. So because we have such a well-defined platform for controlling different variables, we can test different ideas. So just to give you one example, we found that exfoliation can work a lot better if you do the peeling very, very slowly, much more slowly than a human would typically be willing to do if they were peeling it by hand, right? A human gets kind of bored and frustrated and they're just going to peel it off at a certain speed. But we can go much more slowly and very carefully at a constant rate. And it turns out that can help improve the flake. So that's already something we've kind of learned about the underlying physics of exfoliation, just to give one example. Okay, so that's everything I wanted to tell you about. I'm happy to entertain questions if anyone has any.
Yeah, before. You don't have to talk either very loud or you can go talk to the bird.
This is a really interesting talk. My question is, if you wanted to, so this only makes samples for research purposes. If someone found that these 2D materials are useful for some sort of device and you wanted to make them in bulk, this wouldn't be the methodology for it, right? So there's no way to make bulk samples, I guess. Or not bulk samples, I mean like in mass production sort of style. That's my question.
Yeah, that's a really good point. We've definitely optimized it to be a research platform. Yeah, so it's for people to kind of accelerate their research, try different ideas, all of that kind of stuff. But I think like, so you're right. If you wanted to build, really mass produced, if you found some 2D material that was awesome and you really wanted to mass produce it, you would want to build a different kind of tool. But I do think that your question is insightful, because I think one of the underlying ideas in QPress was that the knowledge we gain in building this robotic automated system is the kind of knowledge you would need if you eventually wanted to build like a true industrial version of it, right? So like if people are really going to use 2D materials in real quantum devices that are sold, they're gonna have to be able to fabricate them very efficiently. And so these kinds of ideas, like this roll-to-roll version of exfoliation rather than doing it by hand, those are going to be necessary. So I don't know what the final industrial version of it would look like, but I hope that our research is a stepping stone in that direction. Like it lays the foundation to allow people to eventually build those commercial tools if they indeed are necessary.
There are no other questions, and let's thank Kevin.
Thanks, everyone.
We appreciate